So this could be like a possible maybe free response question or a multiple choice question on the upcoming exam next week, probably late next week. We got the limit as x goes to 2 from the left-hand side of that beautifully factored rational function. So remember, if we look at it, we could try direct substitution, right? Direct substitution is going to give you 5 over 0. And 5 over 0 is dne when it comes to the function, right? The function value doesn't exist. But this sheds some light on what's going on then at 2 for that function, because non-zero over 0 implies that there's a what there graphically? A vertical asymptote, yeah. And a vertical asymptote means that your y values are either going to increase without bound or decrease without bound. So remember, if this were a free response, non-zero over 0, you could say what as a correct answer and be technically correct? dne, yeah. So on a free response, that would be fine. But if this were a multiple choice question, non-existent or dne would not be an answer choice, so you'd have to do better than that. So what are the other two options, as we already said? One of infinity or negative infinity, yeah. So at least on a multiple choice, some people who knew there was a vertical asymptote there for a one-sided limit could maybe get a 50-50 shot, but y'all could do better than that, right? We don't have to guess, because we know, even without knowing what this graph actually looks like, we can figure out the sign of the infinity by choosing a number such as 1.9. Yeah, I wouldn't go further than a tenth away. Okay, the idea being if you're so close to the vertical asymptote, you're already well on your way towards the type of infinity, at least on the correct side of the x-axis. So if you plug in a 1.9, look at the sign that you're going to get. In the top, 1.9 plus 3 is positive, and in the bottom, 1.9 minus 2 is negative, and 1.9 minus 1 is negative, right? So in the bottom, you have negative times negative, which is positive.
1.9 minus
1. Oh, it's positive. Yeah, very good. Very good. It always has been. It always will be. 1.9 minus 1 is positive. Okay, so now we have a positive over a negative, which means the whole ratio would be negative. Yeah, so the answer is negative infinity. Yeah, sweet. Now, in this case, I kind of came up with this example because if you pick a number to the left of 2, like 1, would that work? No, if you plug in a 1, you see that you get, oh, that's going to be dne again. So maybe you go further to the left of 2, like 0. Right? What happens if you plug in a 0? You get positive over positive, which is positive. Reason being is because there's a vertical asymptote not only at 2, but also at 1. And so if you pick a value to the left of 2 that's to the left of 1, you're way too far away. So when in doubt, just pick a number that's immediately to the left or to the right. And you could probably say by a tenth, right? Unless that was x minus, that was something that was a tenth away, like 1.9, but it's not. So anyway, comments or questions on that? And the fact of the day is 1.9 minus 1 is positive. Okay, there you go. I learn new things every day. We make careless mistakes every day, don't we? All right, so it's really about minimizing the careless mistakes. All right, any other comments or questions before we start 1.2? This section should go pretty quickly. Properties of limits, properties of limits, properties of limits. Okay, so here are some properties of limits. This is the algebra of limits, if you will. Addition, subtraction, okay? So if you're taking a general limit, they also work for one-sided, of the sum or the difference of two functions, the algebra says you could take the limit of each function independently and combine the results, okay? So it's almost like you're distributing the limit, right? The limit of a sum is the sum of the limits. That's what this says. And so this gives us a way to maybe like divide and conquer. If we have the limit of a large function with many, many, many terms, we can kind of like take the limit of each term or combination of terms separately and then combine the results. The second one is the constant multiple rule. If you let k be some constant with a k, and you want the limit of a constant times a function, constant multiples, you hear me say this a lot this year, they'll go along for the ride. They're there in the beginning, they'll be there in the end. You could essentially pull them out front, take the limit of the function, and then take the result and multiply it by a constant. The next one is multiplication, and this one's kind of cool. If you have the limit of a product of two functions, it's the same as the product of the limits. You can take the limit of each function and then combine the results. So in this sense, it's not distributing, because normally we can't distribute something into multiplication. But the limit can basically reproduce itself and go in front of every single variable piece in any expression, and you can evaluate the components separately and then evaluate it, okay, at the end. And it works the same thing with division. The limit of a quotient is the quotient of a limit. So you could take the limit of each function, the top or bottom independently, get the results, and then divide them out, of course, assuming you're still not dividing by 0. This would be the exponentiation rule. Let's say you have a function raised to a large power. You could bring the limit inside, and you could take the limit of the function first, and then take that result, and then exponentiate it. Okay, so again, what we're essentially doing in each of these is we're bringing the limit and we're putting it directly in front of every single variable piece in an expression. And we'll see this in action here in just a second. All right, this last rule is probably one of the most interesting ones, if not important. Composition, right? Remember, composition is like f of g of x or g of f of x. Think of this as like a sequence. Okay, so let's say we have the limit of a function g as we go to c is equal to L, right? Some letter L. Then how can we find the limit as x goes to the same x value of a composite function f of g of x? F of g of x, okay? So here's what we're going to do. I'm going to write an intermediate step. In the same spirit of what we've been doing, we can take this limit and we can bring it to the inside. And so this would become f of, and then we can evaluate the limit as x goes to c of g of x, right? We bring it inside, kind of like order of operations. We would do that first. And of course, we were told that this inside limit is equal to what? We were given that that equals what? L, right? So here's the only thing. We cannot just do a direct replacement. We cannot say that that equals f evaluated at L. Why not? What does f of L represent? A road or a bridge? It's a bridge, right? And we're calculating limits, so we're calculating roads. So instead of f of L, which we can't do, L is still going to be our input, but it's going to be the new input that we're approaching, okay? So now it becomes the limit as x approaches L of that function f of x. We have to keep it in the context of a limit, okay? So it's like we're substituting, but we're substituting a limit input, not a function value, okay? And this thing works from either side. If they're one-sided limits, we would keep it as a one-sided limit. So if we started from the right-hand side, we would keep it as a one-side. Okay, it works for left and right and general limits. Okay, so we'll see how to do that one there, right? And it's kind of a notational thing, but you could get in trouble. All right, so you don't need to write this down, but here's kind of a combination of all those rules. This is how we're going to use it. Let's say we have the limit as x goes to c of that big blob, right? We've got x, f of x, we've got an x in the bottom, and g of x squared. That's what that means. If you ever see like g squared of x, that's the same thing as the function g of x quantity squared. That's condensed notation. It's like sine squared of x instead of sine of x quantity squared. So that's what that means. So if you look up there, we have 1, 2, 3, 4 different variable places. You can actually put the limit directly in front of each of those, directly in front of the x, in front of the f of x, in front of that x, and in front of the g of x, okay, which I showed over here on the right-hand side. And you're going to essentially evaluate each of those independently, hopefully replacing those with values, and then you're just going to simplify that numeric expression, okay? So it's kind of like divide and conquer, right? All right, so you don't have to write, that's not really a property, but that kind of embodies all the properties. All right, let's try it out. Here's an example that deals with these properties. We're going to have information about unknown functions, which is why the properties are going to be useful. Let's say that we're given some limited information about two functions f and g. We know that as we approach 3 from both sides for the function f, we're getting closer and closer to 8. And as we approach g from the same x value from both sides 3, we're getting closer to -2. Oh, and we have this third function, h, that as we approach the same x value, 3 from both sides, we get closer and closer to 0. That is all we know about those functions. Do we know if those functions are continuous at 3 or not? No, because all we have information about is the roads. The function value, which is the bridge, may or may not exist. We just know information about the general limits. Now we can find the limits of the following that exist, okay? So here we go. Example A, the limit as x goes to 3 of twice f minus 4g. We don't know what f and g are, but because we can divide and conquer, here's what it's going to look like. We could take the limit, essentially, and put it in front of the variable pieces. So this is how you could rewrite it. 2 times, that's the constant multiple rule, bring it out front, the limit as x goes to 3 of f of x and then minus 4 times the limit as x goes to 3 of g of x. So that would be using the first rule, the sum and difference rule, combined with the constant rule, bringing the coefficients out front. Now this line right here, this is an optional line for you. If you don't want to write that, you don't have to write that. But this is why the properties work. Okay, because what I've done is I've narrowed it down to information that was actually given to us, right? So now it's just a matter of substituting. So what is the limit as x goes to 3 of f? 8, right? Minus 4 times the limit as x goes to 3 of g is negative 2. So at that point, we could substitute in, and then we just combine it from there. Free response, you're done, right? If this were a free response. Multiple choice, you keep going. That's 16 plus 8, which is 24. And again, notice the way I work this. It's an expression. There's an equal sign up there. But if you work straight down beneath it, you don't need to put the equal sign. Okay? And the bottom line is your answer. So in the future, as long as you know you're substituting limit values, you could go straight to this line right here. Okay? But you'd have to be careful. Like if I had said f of 3 equals 5 instead of 8 for the limit, you would want to make sure that when you replace f of 3, you're replacing the limit with 8 and not the function value with 5. Does that make sense? So as long as you understand, it's limit information, not function value information, you're in good shape. Okay? Letter B. Go ahead and try this one on your own. And if you feel like you're already ready to skip that property step, the rewriting, go for it. I'm going to go ahead and write it. Think you got it? Look up there and see if I got the same answer as you did. If I did, it means I'm probably right. Because I trust you all a lot. All right, so that first line with the asterisk, that's the optional line. That's the one where you're rewriting it using the properties. Okay, but essentially you get it down to this piece, which you then substitute from the given information, which is negative 2, and then it's just a matter of a multiple choice question using your Aunt Sally's rules to simplify in the proper sequence, because there's still a lot of ways to mess that up. So again, remember, if this is a free response question, you're done right there. If it's a multiple choice, you got to keep going. All right? So good so far? No big deal? All right, moving along. Same thing here. Go ahead and do this one on your own. If you wrote the optional line on the last one and you want to keep doing that, that's great. If you want to try and skip that step on this one, that's okay too. I think I'm going to do that. I'm going to skip that one. Okay, so every x that appears in the expression is going to be a limit value, not a function value. I didn't give you any function values. I only gave you limit values, so you could go ahead and substitute. So the cube root of the limit as x goes to 3 is the cube root of 8. Substituting that in. The limit as x goes to 3 of g is negative 2. And the top, 4 times the limit as x goes to 3 of h is 0. And on the bottom, what do I do with that x? Plug in a 3. Yeah, very good. So I'm giving you a function here, x plus 7, that you actually know something about, right? That's the graph of a line with a slope of 1, and it's continuous everywhere. So at any point, the function value is the same as the limit value, right? So essentially, you're using direct substitution there. So you do just plug in a 3. Now, if this were a free response, could you stop here? Yeah, as long as it's a number that actually exists, you could stop there. If it's a multiple choice, you can keep going. That's going to be 2 over negative 2 plus 0 over 10, which of course then is negative 1. 0 divided by any non-zero is 0, so the answer is negative 1. You would want to be careful if that expression up there was actually non-existent. Then if you leave it like that and don't say D and E, now it's wrong. So anyway, there you go. So far so good. Not a big deal, right? So that's one type of question. You're going to be given some information about limits, maybe some distracting information like function values, but you can just use direct substitution, okay, with limit values. All right, so here's another way that the same type of questions could be asked. Instead of giving you just limited information, you could be given graphs of functions like f and g, and now we have a little bit more variety here. We can pull values from different x values instead of just using the same one every time. All right, so let me walk you through one like this. The limit as x goes to 0 of twice f squared plus 3g. So again, here's the graph of f on the left, and here's the graph of g on the right. If you're ever given graphs like this, and there's nothing that's actually said about the true values, if it appears to cross at an intersection of two integer grids, you can assume that it is, okay? All right, so here's what the step would look like. I'll probably do it one more time here. This is going to be 2 times the limit as x goes to 0 of f of x, and then that would be squared there. I guess we don't need those extra set of parentheses. We'll get rid of that one. All right, so there's that one, and then plus 3 times the general limit as x goes to 0 of g of x. All right, so then to get it down to here gives us now something that we can either substitute with given values or pull from the graphs of f and g respectively. So they're both approaching 0 from both sides. So let's do the f1 first, and just make sure you get the right graph. That's the one here on the left. The general limit at 0 would be what? 2. Yeah, we're approaching from the left, we're approaching from the right. It appears to be continuous, but regardless of that, the y values are appearing to approach 2. So it becomes 2 times 2 squared. Plus 3, and then the limit as x goes to 0 of g. We move over to this graph, and it appears that the limit at 0 is 0, right? I drew those, so yeah, it looks like it's passing through the origin. You can assume that it is. So there you go. There's your free response stopping point, because it exists. And of course, if it's a multiple choice, you just be careful. It's 8 plus 0, which is 8. Yeah, no big deal, right? Almost as easy as the first one. All right, so go ahead and do B on your own. I'll do it with you. So again, the option would be to rewrite the limit 3 different times in front of each of the x squared, which we know is the parabola that's continuous, the g and the f. So the x squared again, which is continuous, direct substitution works. So that's going to give you a negative 3 quantity squared, which you got to be careful with your negatives here, right? Because that's going to give you a positive 9. And then the general limit of g again is the one on the right. So as we approach negative 3, and again, I apologize for my lack of horizontal, but we can assume that it is a horizontal line. We'll assume that my drawing indicates it's 1. And then the bottom we have f from both sides. And so here's negative 3 here, and it looks like it's there. So again, you can assume it's negative 1. So when you plug in, of course, free response, you're done. But if you carefully evaluate all the negatives, you're doing it with negative 9. And so, of course, you could probably predict what another answer choice would be on the multiple choice portion of the test. Positive 9, right? Yeah, for sure. Okay, so it's not very difficult. So let's move on to part C now. How do you read that? G times F? G of F, right. That's a pre-cal thing. Okay, G of F, right? So this one is composition. So if you are going to be using the properties to rewrite it, the composition one is the one where I think is probably worth doing it. So bringing the limit inside, we're going to have G of, and we're going to have the limit as x goes to -3 of f of x. So again, it's okay to do it without it, but this just makes it a little bit easier because this is a sequential thing, okay, not just like combined results, sequential. So now we go to the inside, and we're looking for the general limit of f at -3, which we already said was -1, right? -1. So this becomes g of -1, correct? I just substitute that. Is that correct? No. You do that, and you're going to take the bait. You're going to be a statistic. That's a different class, okay? It's not equal to that. So -1 is still our input, but it's now the input for the limit on g. So if you're going to write that correctly beneath there, now it's the limit as x goes to -1, and it was a general limit, so it stays a general limit of g of x, okay? So remember, we write our inputs differently for function value and limit values. Let's see if it even matters, right? That possibly can't matter. Function values and limits being different? Oh, yeah. Yeah. The function value is 2. What's the limit value, though? Oops. 1, right? So, yeah, there is a huge difference. So the answer is 1, and, of course, a nice distracting answer would be 2 on a multiple choice. So be careful, right? As long as you keep it in the context of the limit, it's just sequential. Your inputs yield an output. That output becomes a new input, but a limit input. So notation is pretty important, all right? It's equal to, if you want to kind of complete the notes. Sequence. All right. So good so far, so good. Any questions? All right. Well, let's see if we can hammer these out. Do this one on your own. And I'll write the steps up here. I'll just do it quietly along with y'all. This one's another composition because it's not just g of x, not g of f of x, but it's g of x squared. So x squared, bring it inside. Again, we know that's a parabola. It's continuous, so the limit's the same as the function. So you can evaluate that limit by direct substitution. So -1 quantity squared is 1. But again, if you get into the habit of just making that replacement in the same physical location, you can get bitten, right? So it's not equal to g of 1, but rather 1 is now the new general limit as we approach x on the function of g, which then you come back over here and you look at it, and it looks like in this case you would be safe if you accidentally called it the function value on a multiple choice because it looks like it's continuous. But if this were a free response and you call it g of 1 and then got the right answer, you would still lose points because it's not equal to g of 1. So there's always a penalty for mathematical prevarication, which is lying mathematically. All right, so notation is very important. All right, go ahead and finish up the last two. Do them on your own, and I'll try and work them with you, and we'll compare answers. These are one-sided limits now. If you're done, check my work. So I give you the free response stopping point and the multiple choice stopping point. Everyone agree? Anyone disagree? Sometimes I make mistakes on purpose. Have a great lunch. Have a great lunch.